Hi everybody. In this video I want to do an example in which I find the magnetic field due to two long currents. How long? Approximately infinitely long. Alright, so here's the problem. Imagine I've got an x direction to the right, a y direction upward, and a z direction out of the board. Alright, I imagine I have passing through the origin right along the z-axis an infinitely long current with the current going in the positive z direction. So coming right out of the board. Imagine that running parallel to that long current, I have another long current, D away, capital D away on the x-axis. We're taking capital D to be a positive number. So passing through the location D, 0, 0, I have another current running parallel to the z-axis, also coming out of the board, out of the page. All right, so I1 and I2 are those amounts. These are the directions, positive z direction of those currents. The little dot, just imagine we're looking at the currents head on as they're coming out toward us. All right, so our job is to find the magnetic field at the location x equals 0, y equals minus b, where b itself is a positive number, so minus b will be a negative number, and then z equals 0. All right, so that's somewhere along, that's basically on the y-axis, an amount b below it, so this is at location y equals minus b, right there. So we want to find the magnetic field at the location of the red x. Okay, so basically magnetic fields in this way, in this example, will work the same way that electric fields work. Remember back when we dealt with electric fields, if you have the electric field, if you've got a charge here and a charge here and you want to find the electric field right here, you find the electric field at this location due to this charge, you find the electric field at this location due to this charge, and then you just add those electric field vectors up as vectors. Well, same thing here, except now we've got magnetic fields. So if I want to know the magnetic field at this location, I need to find the magnetic field that I1 produces right here. I need to find the magnetic field that I2 produces here, and I find the net magnetic field by adding those up as vectors, because magnetic fields are vectors. All right, so what we need to do is apply the magnetic field due to a really, really long current twice, basically, and add up those results and add them up as vectors. So the magnetic field due to a really long current, we've got a physical constant, mu naught. We've got the current in the numerator, the perpendicular distance from the current to where we want to know the magnetic field in the denominator, the factor of 2 pi. And the direction is by the right-hand rule, a derived right-hand rule, which I'll go over again in a moment. Okay, so let's do this. So let's first find the magnetic field that I1 produces right here. First I'll figure out the direction. Now remember, if you've got a long wire, the magnetic field basically makes circles around that long wire. Which way do the circles go? Well, the right-hand rule tells you which way. You stick your thumb in the direction of the current and your fingers will tell you which way the magnetic field goes. So if the current's coming out, I'm just going to put it right here so you can visualize it. Stick my thumb of my right hand in the direction of the current, my fingers wrap around. All right, so that means the circles go around this way. Same thing right here, all right? Thumb of my right hand in the direction of the current, my fingers wrap around, the circles go around this way. So at this location right here, as I'm following a circle, the magnetic field will be completely in the x direction. I should say that's the magnetic field contribution from current 1, so I'll call that B1. How do I know it's exactly this way? Well, because this has to be a right angle. To be on a circle is to be perpendicular to a radius. All right, so from here to here, that's like a radius. That's our R1 perpendicular from current 1 to this location. Magnetic field's got to be perpendicular to that basically radius of this circle. Great. All right, while we're at it, let's go ahead and figure out the magnitude. All right, so this is a vector, magnitude and direction. I know the direction has to be the positive x direction, so I'll put that right here. Now we'll figure out the magnitude. All right, so I need to basically use this formula. I have my mu naught. I need the current that's producing this magnetic field contribution. That's this current, so I'll call that's I1. I need my factor of 2 pi, and then I need the distance, the perpendicular distance from the current producing the magnetic field to the location where I am finding the magnetic field. All right, this magnetic field contribution is coming from this current, so I need the distance from this current to this location where I want to know the magnetic field. So that distance is b. The y-coordinate is negative b, but the distance is b. Great. So here's the magnitude of the magnetic field, and there's the direction. Okay, we'll do the same thing, and that's the contribution to the magnetic field from current 1. We need to find the contribution to the magnetic field at this location from current 2 as well, so I'll call that B2. To help me, I'm going to draw a little line from current 2 to this location. This would be my R perpendicular from I2 to this location. I can call that R2 perpendicular if I want, and I'll figure out that distance. In fact, I might as well figure out that distance right now. This is the hypotenuse of a right triangle with sides D and little b, so that distance will be capital D squared plus lowercase b squared, quantity square rooted. Okay, great. Now, so I know the distance from here to here. I can figure out, you know what, I'll figure out the magnitude of this magnetic field. Let's do that. So at this location, I'll have a B2. I'm going to get the magnitude first in this case, and we'll worry about the direction. B2, well, so B2 is going to represent the magnitude of the magnetic field that I2 produces right here. I don't have a vector symbol over it because I'm just going to do the magnitude first. All right, I'll use the magnitude formula for the magnetic field due to a really long wire. Mu naught. Now, for my current I need the current that's producing the magnetic field. I'm talking about contribution B2, so I need I2 over 2 pi, and I need this R perpendicular. That's going to be square root of lowercase d squared, uppercase d squared plus lowercase b squared square root. Great. So that's the magnitude of the magnetic field that this thing produces right here. What about the direction? Well, we know that the magnetic field that this long wire produces is going to make circles around that long wire. So if I've drawn myself a radius of those circles from the wire to the location I want to know the magnetic field, the magnetic fields are going to be perpendicular to that radius. They'll either be this way or this way. Which way will they be? Well, the right-hand rule will tell us. Stick your thumb of your right hand in the direction of the current. Your fingers wrap around. When the fingers intersect this line, they're going this way. So B2 has to be this way. And I'll just write that. B2 vector. Okay. I know B2 magnitude. I know this is the direction of B2 vector. Just remember, this is a right angle right here. I'll put a little right angle reminder. B1 is completely in the x direction. B2 is partly in the positive x direction, partly in the negative y direction. All right, so we need to break that into components. I'll write those as little red arrows. So this will be B2x, and this I'll write as B2y. B2y will be negative, B2x will be positive, and B2x and B2y would be the sides of a right triangle where the hypotenuse is B2 magnitude. Okay. What I need to break this into components is I need an angle. I often like to use the angle from the x-axis. So if I had, for example, this angle right here, which I'm going to call theta, I would have a right triangle. I'd have this leg, and then my hypotenuse. Okay, so B2x would be B2 times the cosine of theta, because that's adjacent. B2y would be B2 times the sine of theta. So I'll even write those in. B2x will be B2 magnitude cosine of theta. And I got to be careful. I almost left out a minus sign. I know B2y has to be negative. And so I wrote down B2 sine of theta, but B2 represents a magnitude, so it's positive. Sine of any angle between 0 and 90 degrees will be positive, but this has to come out negative. It's clearly in the negative y direction, so I need to put in that minus sign by hand. Okay, so our job then is to figure out the sine and cosine of this angle. Now, we could do that if I had all the, if I had a set of numbers, I could figure out that angle, then I could compute the sine and the cosine. This is a completely symbolic problem, so it's a little more complicated. But what we can do to get a nice analytical result for this symbolic problem is I can relate this angle, which, I don't know the relative sizes of things in here, to an angle in here, for which I do. Little b is given. I don't know what it is, but it's a given symbol. Capital D, I don't know what it is, but it's a given symbol. I could express the cosine and sines of angles in this triangle in terms of ratios of the sides of that triangle. So if I could relate this angle to an angle in this actual triangle here, then I could figure out the sines and cosines. So let's do that. This must be a right angle because B2, remember, makes circles around I2, and so to be on a circle is to be perpendicular to a radius. Here's your radius. So this is a right angle. So that's 90 degrees. If this is theta, then the remaining part must be 90 degrees minus theta. Meanwhile, this is a right angle, and if this is 90 degrees minus theta, this remaining part here must be theta. All right, so just to go over that again, here's a right angle. 90 degrees minus theta plus theta gives me 90 degrees, so that checks out. Here's a right angle. 90 degrees minus theta plus theta gives me 90 degrees, so that checks out. Great. All right, so this theta I can work with. So here's the trick. The cosine of this theta has to be the same as the cosine of this theta because it's the same theta. Meanwhile, the sine of this theta has to be the same as the sine of this theta because it's the same theta. So let's just take one more step. Cosine of theta will be cosine of theta. Cosine of theta will be adjacent over hypotenuse. So I'll have B2 cosine theta, which would be lowercase b over the square root of capital D squared plus b squared. Meanwhile, I can do the same thing here. I've got my minus sign. I can't forget that. I got magnitude B2. Sine of this theta is the same as sine of that theta. Sine of this theta will be opposite over hypotenuse, so that'll be capital D over square root of D squared plus B squared. All right. So now we're in good shape. I can put my B, I can plug in for B2, so I'll do that here. I'm going to have mu naught I2 over 2 pi square root of D squared plus B squared. Then I'm going to have little b over square root of D squared plus B squared. Likewise right here, I've got my minus sign. I've got my B2, which is mu naught I2 over 2 pi square root of D squared plus B squared D over square root of D squared plus B squared. Okay, so I've got only a couple more steps. One thing I need to note, and I'll put it right here. All right, B2y is this, which is this. B2x is this, which is all of this. But B2 vector would just be B2x x hat plus B2y, y hat. All right, so I'm going to have to do this in a couple of steps because I'm going to run out of space. But here we go. So the net magnetic field at this location, which I'll just call B vector, will be B1 vector plus B2 vector. I'm just adding up all the magnetic field vector contributions at this location produced by all the current segments. I happen to have two of them, so I've labeled them 1 and 2. I'm adding those as vectors. All right, but now I can start putting in these expressions. That'll be equal to, B1 is a vector. I'll write it this way. All right, this part is just B1 vector. B2 vector is B2x component x hat plus B2y component y hat. So I'm going to write those out now. This thing and this thing, the square root of this plus square root of this will just be what's left under the square root. All right, so B2x is this, where I've taken this, and square root of a quantity squared is just that quantity. And then all of this is in the x direction. So now do the same thing for the y part. So I'm going to have this times y hat. When I take square root of d squared plus b squared times square root of d squared plus b squared, I'm just going to be left with d squared plus b squared in the denominator. So here we go. All right, so this is the answer. It looks like a mess. We can clean it up. It would be nice to write this, my net electric field, as stuff times x hat plus other stuff times y hat. So I'm going to do some factoring. In addition, I can factor out a mu naught over 2 pi from every single term. So what I'm going to have is mu naught over 2 pi times some quantity of stuff times x hat plus other stuff times y hat. So I'm just going to take a moment to clean that up. Okay, let's just double check this. So I did some factoring, but we can always make sure that what we have is equal to what we had. All right, so if we factor mu naught over 2 pi, multiply mu naught over 2 pi back through, mu naught over 2 pi times all of this gives me this. That looks good. Then if I multiply mu naught over 2 pi through here and also distribute both of those onto the x hat, this and this and this gives me that. This multiplying by that gives me this. So it all looks good. There's some other checks we can do. Sometimes when people look at a problem like this, they say, wait a minute, Dr. Looney, we've got just a b in this denominator, a length, but we've got a length squared down here. But careful, look at the numerators. Here I have no length in the numerator, I just have current. So this right here is current over length. This here is current times length over length squared, which reduces to current divided by length. So the units of this and the units of this are in agreement. That's good. Anytime you have two things that are adding together in a physical expression, those things better have the same units. All right, same thing here. I've got current times length divided by length squared. That gives me current over length. Let's just double check that, right? So we should overall have mu naught times current divided by length divided by 2 pi. That's in agreement with our baseline formula for the magnetic field due to a single current. Okay, so hopefully that helps. Just to recap the main points, magnetic field is a vector. If we have a magnetic field produced by multiple current segments, what I need to do is work out the magnetic field at the particular location of interest produced by each of those current segments. Magnetic field is a vector, so there will be amounts and directions. If my two vectors are in different directions, I either have to have a way of writing them in terms of x hat unit, y hat, z hat unit vectors, which I've done here. An intermediate step into doing that is if I knew a magnitude and a direction, I can work out the components. Some key steps: be careful of signs. Remember, I almost lost this minus sign right here, but that's very important. Hopefully that helps. Thanks for watching.